Good morning, everyone. This is my dog Pepin. Say hi, Pepin. He's doing much better after his eye surgery. His cone is finally off, and we're down to eye drops twice a day instead of 4 times, so we're all very happy about that. He's very happy about us being home and stuff, so I thought I'd introduce you. He's an old man, but he's a good boy still. He's very confused, doesn't know where the camera is. Can you look at the camera? Very confused. Anyhow, today we're doing notes on energy and phase changes. Sorry, I gotta take care of my dog. So these notes are available on Classroom. You can print them out and fill them in, but I do pre-record, so you can always go back and do notes later if you don't get to it right now. Okay. So this is a heating curve that we see. It's not actually a curve, it's more of a line, but you'll see solid, liquid, and gas phases. This is a point where temperature is increasing, but everything in the sample is still solid. Here, temperature is again increasing, but everything's liquid, and here's temperature increasing, but everything is gas. Where it plateaus here and here, that's where the actual phase change occurs. There's not actually a temperature change when things are melting or when things are boiling or condensating or freezing. At that point, all the energy that's being input into the system or taken away from the system as heat is going into breaking intermolecular forces, okay? So remember, phase changes aren't chemical changes, they're physical changes. So we don't see any chemical bonds breaking, but we do see intermolecular forces changing. Okay, so that's one way to distinguish chemical versus physical changes. Are intermolecular forces changing, or are chemical bonds changing, being broken or formed? Okay. So energy has to be added to a system for a solid to liquid or liquid to gas phase change to occur, so the energy of the system increases. For the opposite to happen, whether for a gas going to a liquid or a liquid going to a solid, the energy of the system is going to be decreased, so it's removed from the system. And that energy is again between intermolecular forces, not necessarily between chemical bonds. For temperature, temperature changes during phase changes don't occur, again, because that energy is going into the extension or weakening of intermolecular forces, or from the actual severing or breaking of intermolecular forces. So that's the point in the heating curve where it actually plateaus, okay? So when we're boiling water, if you add heat, that increases the amount of time or decreases the amount of time it takes for things to change to the gas phase, but that boiling water itself is 100 degrees Celsius at 1 atmosphere. So there's not actually a temperature change occurring while you're boiling water until all that water turns into a gas. Then the temperature change could occur. But during the phase change, no temperature change is occurring. Okay. So this is a cooling curve. So it has the states of matter there, liquid and solid, and solid. Again, where it plateaus, that's where both liquid and solid are in the same phase. So that's during the phase change. We start with all liquid, and then when everything turns to solid, that's where we have here. This dip here is super cool before they solidify. So during supercooling, the substance remains in the liquid phase after the temperature has dropped below the freezing temperature. So at the bottom of this curve, solid crystals form, which causes the temperature of the system to increase dramatically as heat is released by the solvent particles during the process of solidification. Okay, so the solidification process is exothermic. It releases heat because the system is losing that heat. So in solids, molecules are held close together in a regular pattern by intermolecular forces, which are depicted as the red dotted lines here. Okay, so these are all intermolecular forces. They line up in a regular pattern. Negative poles are attracted to the positive poles of other molecules, and it results in a strong dipole-dipole attraction that maintains the organization of this structure. So since these molecules have dipole-dipole interactions going on, basically. So they're drawn here. Again, the dipole-dipole interaction as a red dotted line. But remember that London dispersion forces are also in here as well. Those are the kinds of forces that are present in all substances. So it doesn't matter if it has a dipole or not. Intermolecular forces of attraction are weaker in the liquid phase than they are in the solid phase. So energy must be absorbed in order to reduce these intermolecular forces. From the name fusion, you might assume that the molar heat of fusion, this delta H fusion, is the heat lost as 1 mole of liquid becomes solid, but it's actually defined as the heat gained as 1 mole of solid liquefies. Okay, so this is the change as solid is liquefying, not as liquid is solidifying, if that makes sense. So that's how we actually define it. So the energy released when 1 mole of pure liquid solidifies is equal in magnitude, but then it would be opposite in sign as the delta H fusion. Okay, for ionic compounds, we obviously have ionic bonds, which is a stronger intermolecular force than dipole-dipole or London dispersion forces. So the delta H fusion values for ionic compounds are very large. Okay, so here's kind of an example. We're saying that it's equal in magnitude but opposite in sign. So here, melting water going from solid to liquid, the enthalpy of fusion is equal to 6 kilojoules for every mole of water you have. For freezing water going liquid to solid, it's going to be negative 6 kilojoules for every mole. And this energy diagram kind of shows that process. So going from liquid to solid, we're releasing 6 kilojoules per mole of water, but going from solid to liquid, we're taking in or gaining 6 kilojoules for every mole of water that is going from solid to liquid. So here we have an example. How much heat is required to melt a 5 mole pure sample of ice at 0 Celsius? Okay, so remember that the unit that we're going to be looking for, how much heat, is going to be in joules or kilojoules. And for this enthalpy of fusion for water, it's 6 kilojoules per mole. Okay, so going from solid to liquid, it's going to be 6 kilojoules per mole. We're not interested in kilojoules per mole. Our final answer is going to be in kilojoules. So here's when you can kind of think, when in doubt, cancel out. How are we going to end up canceling out this mole here? So to do that, we're going to take our 5 moles of water that's given and multiply by our enthalpy of fusion, 6 kilojoules over 1 mole. That will cancel out our moles, and then we get 30 kilojoules of heat required to melt a 5 mole sample of ice at 0 degrees Celsius. Okay, this occurs at 0 degrees Celsius because remember in our heat diagram, that's where the actual physical change is occurring. So that's where the ice is going from solid to liquid. Then we have this example. How much heat is required to melt 2.5 moles of aluminum that's at 290 Kelvin? Aluminum melts at 933 Kelvin, and the heat of fusion for aluminum is 10.7 kilojoules per mole, and the molar heat capacity of aluminum is 24.3 joules per mole Kelvin. So this problem obviously has a little bit more kind of going into it here. So this is going to be a multi-step problem. Okay, so step 1, we need to find the heat that's required to change the temperature of the aluminum to 933 Kelvin. Okay, so our starting temperature is 290 Kelvin, and our final temperature, where it's going to actually start to melt, is 933 Kelvin. To do that, we're going to find the change in temperature from final minus initial, which is going to be equal to 643 Kelvin. Then we take our 2.5 moles And we're going to be using the heat capacity because remember, that's how much energy it takes to change a substance, 1 gram of that substance, by 1 degree Celsius or 1 degree Kelvin. Okay, so we're going to take our moles that we have, 2.5, multiply it by the heat capacity, and then multiply it by our change in temperature that we have to have occur. Okay, so to actually bring the heat to 933 Kelvin, it's going to take 39,100 joules of energy or of heat. So that's what it takes to bring it to that melting point. Now we have to figure out the energy it's going to take to actually melt that 2.5 moles of aluminum and add it to this energy that we just found here. So step 2, add the heat of fusion for aluminum. So again, we have 2.5 moles of aluminum, and then its heat of fusion is going to be 10.7 kilojoules per mole. So we're going to find how many kilojoules that is. 65.9 kilojoules. Okay, now we can add these two values that we found in step 1 and 2 together. But remember, here we have kilojoules, and in the example before, we had just joules. Okay, so we have to make sure that they are in the same unit before you can add them together. But luckily it's kilo, so you'll either multiply or divide by 1,000, depending if you want your answer in kilojoules or joules. For liquids, in a liquid, the same intermolecular forces of attraction do exist as before, but they're not as strong as they were in the solid phase. Okay, so we have kind of longer interactions here. So they are weaker than they were in the solid phase, but they still exist. So we still have these dipole-dipole interactions, and we still have the London dispersion forces as well that are present in everything. Okay, when we get to the gas phase, ideally there's no intermolecular forces, but in reality there are some that do exist. So now we're going to talk about enthalpy of vaporization, which is the heat absorbed as 1 mole of liquid becomes gaseous. Okay, so in gas we assume that the particles have no intermolecular forces of attraction again. In a liquid, the attractive forces are still pretty large, they're still noticeable. So heat must be absorbed in order for the molecule to enter the gas phase. This is why you feel cold when you get out of water. So the heat required to evaporate the water is pulled from your body and cools you down. So this is why you sweat. This is why you feel good when you get out of the pool in the summer and it feels cooler out, even though the temperature outside is still the same. That water is basically just taking energy, heat from your body and releasing it to the system, which makes you feel cooler. So the energy released when 1 mole of pure gas condenses is equal in magnitude but opposite in sign. So same idea as the heat or enthalpy of fusion that we saw before. If we're going from a gas to a liquid, equal in value but opposite in sign. So here again we have liquid water going to gaseous water. It's going to take 41 kilojoules for every mole of water. If we want to condense water, that would be going from gas to liquid, not solid to liquid, but it would be negative 41 kilojoules per mole. So go ahead, be sure that you change that to gas and not liquid there. Just wrote the wrong thing. That's melting, not vaporization. But again, equal in value, opposite in sign. And here's our energy diagram that kind of shows that. Here we have going from gas to liquid, we're going to be releasing energy. And going from liquid to gas, we're going to be taking in energy to make that phase change occur. So here we have an example. How much heat is required to vaporize 2 moles of water at 298 degrees Kelvin? Heat of vaporization for water is 41 kilojoules per mole, and the molar heat capacity of water is 75.4 joules per mole Kelvin. Okay, so this is again going to be a 2-step problem. We have to figure out the heat that's going to take to bring the water to 100 degrees Celsius, and we have to figure out the heat of vaporization for H2O for this 2 moles of water. Okay, we have 30 seconds left, so I'm going to stop recording and I will jump back in with the solution in the second video.